Okay, so you guys have probably discussed energy in previous science classes. So what is energy? The definition, anybody know? When you think of energy, what do you think about? Electricity. What else? Food. Using force to push things. Those are all examples of different forms of energy. And so energy, the broad definition, is the ability to do work. And so when we talk about energy, we can divide it up into two main categories, and that is kinetic energy. So kinetic energy is energy of motion, how much things are moving. And then potential energy is stored energy. So probably the classic example of the difference between potential and kinetic energy is roller coaster. So at the top, the very top of a roller coaster, before it's about to drop, it will kind of stop. So there, the energy that it has is potential energy. It has the potential to fall, and then as it starts to fall, what happens to the potential energy? It becomes kinetic energy. So that's on a big scale with roller coasters. When we're talking about, for chemistry's sake, we're really looking on the atomic scale. So when we talk about kinetic energy, we're talking about the particles that make up a substance, how much they move. And our way of reflecting that is with temperature. So when we describe the temperature of a substance, what we're really describing at the atomic level is how much the particles are moving. And then potential energy, we said, is stored energy. Well, that's a little bit harder to visualize, right? We know that particles are always moving. But when we're talking about potential energy, in chemistry, we're talking about within the bonds between atoms, the stored energy in those bonds is what we call chemical potential energy. So an example that you're familiar with, gasoline. It contains different compounds that have what high potential energy, meaning when those bonds are broken in the compounds, they're going to release energy. Is that important to us that gasoline contains those high potential energy particles? Yes, that's why we have cars that drive. Many things use gasoline to run, and that is the energy stored in the bonds of the combusted gasoline is changed from chemical potential energy into what kind of energy? Kinetic? Good. The potential energy in gasoline that's stored, some of it is changed or transformed into work. That's what moves the car along. Useful energy in the form of work. Some of the potential energy is converted into heat. Have you ever stood beside a car that's just parked but has been running? What can you feel? Heat. And that heat is another manifestation of energy that was changed from potential energy into kinetic energy. And when we talk about purely running a car with gasoline, the useful work that comes out of it is the kinetic energy to move the car, right? The heat that comes off, we would say, isn't really doing useful work. Now, there are reactions where the heat is useful, but for the most part in chemical reactions, heat is just a byproduct that we want to try to limit. We want more work to be done to move things than to just heat them up. Within a system can be in the form of heat or work or some combination of both. And oftentimes we'll find that it is really a combination of both heat and useful work. And one of you hit on a really useful example of stored chemical energy becoming kinetic energy, and that's electricity. So at the very heart of many chemical reactions is a transfer of electrons, And if we harness that transfer of electrons, we can generate electricity. Useful work. So now we get into this weird word called enthalpy. Try again. So enthalpy, when we describe enthalpy, we're looking at the heat energy change in a reaction. So the heat, when we say heat evolved, that means it could be absorbed, heat energy absorbed, or heat released. Why I did those opposite. Heat absorbed or heat released. So evolved is just a more general term, kind of like involved, but just a little different. So the unit for enthalpy, the SI unit, is joules, just like energy, right? Now, the part out next to it is the different ways that we can describe energy. So when we talk about energy, right, it's the force over a given distance. So a joule is a newton, which is a unit for force, times meters, a unit for distance. We can also look at what a newton is, which is what we've done here, then multiply it by a meter. But what we can also think of energy, a joule, as is pressure, which is what a Pascal is, PA, over a given volume. And that's what meters cubed is. The derivations or the for joule, you don't need to know. Where it will become important is if you decide to move on to IB chemistry, we'll talk about where they come from and why you need to know that. But what might be handy, and I think this is on the formula sheet, but 1 calorie is equal to 4.184 joules. So one way that we describe energy is with calories, and so it would be helpful to know the conversion. Now, notice the C on calories is lowercase. When we're talking food calories, it's an uppercase C, which is really a kilocalorie. So when you look at food and it's got 100 calories in it, it's really got 100 kilocalories. You don't need to know that, but just know that the units got a little wonky. So when we talk about heat, it's a transfer of energy. It's going to be transferred from one substance to another. So what we measure is the change in enthalpy. So the change in enthalpy, right? Do you see the H? That's the symbol for enthalpy. What about this delta? Have you ever seen that before? In math, right? When you were looking at slope, change in y over change in x. So how do you quantify a change? Like when you did change of y, what did you do? So the ending y minus the starting y. So when we do change in enthalpy, we're doing ending enthalpy minus starting enthalpy. But really, we're actually just measuring the change. That we cover in IB chemistry. What you need to know is endothermic versus exothermic. So I'm going to give you we talked about endothermic and exothermic processes when we were talking about reactions. So what do we say an endothermic process means? Energy has to what? Be absorbed, right? So in terms of a chemical reaction, when we say the system, we mean the reaction. So the reaction has to take in heat energy from the surroundings in order for the reaction to occur. And so in that case, the change in heat energy, did the heat energy for the reaction, did it go up or down if it's absorbing heat? Went up. So the change in heat energy or the change in enthalpy is going to be what? Positive. Does that make sense? And we're going to look at graphs that will also help you get this straight in your head. And then what do we say happens in an exothermic reaction? Heat energy is what? Given off. So in more formal terms, the system or the reaction gives off heat energy to the surroundings. So from the perspective of the system or the reaction, what happens to their heat energy? Do they go up or down? Down. So the change in enthalpy or the change in heat energy would be what? Negative or positive? Negative. Okay? So endothermic reactions, we said that energy is what? For the reaction to take place, what has to happen? Energy has to be absorbed. So when we write out the reaction, we can include energy as a reactant, right? If that energy is not given to the reaction and continually supplied to the reaction, then the reaction won't take place. So we said before that the enthalpy change is going to be positive because the reaction is absorbing heat energy. This new part is the potential energy. So we can talk about the heat energy, but that also gives us a reflection of the potential energy of the reactants and products. So if our reaction is absorbing heat energy, then going from reactants to products is going to increase the potential energy. And we're going to look at a graph of this that will help make more sense of it. But the potential energy of the reactants is going to be lower than the potential energy of the products. And when we talk about stability, so from potential energy, we can talk about stability. The lower the potential energy, the more stable. So who's going to be more stable, the reactants or products? Reactants. So lower potential energy, more stable. So some examples of endothermic reactions. Cooking food, right? Put heat energy in. If you stop putting heat energy in, is the food going to keep cooking? No. Thermal decomposition. Calcium carbonate is an example of a compound that when heat is applied, it will decompose into calcium oxide, which is a solid, and carbon dioxide gas. And then photosynthesis. For photosynthesis to occur, what has to be provided? Sunlight and some heat, right? And so photosynthesis is another example of an endothermic process. Yes? Okay? So next we're going to look at potential energy diagrams. So if you'll just label, this is a potential energy diagram. Let's talk about it before you draw it so we can look at the features, because it's a little bit weird if we haven't talked about it. So on the y-axis, what do we have? Potential energy. And on the x-axis, we have the reaction progress. So where we're going to start, if we're looking at reaction progress, what are we going to be starting with in a reaction? What do we call those things? Our reactants, right? And then if we look at this potential energy graph, we see that the potential energy is going up, and then it goes down just a little bit, and we get to our, what do we end up with? Products. So if we look at this potential energy diagram, who has a higher potential energy, our reactants or our products? Products. So are our products more stable or less stable? Less stable. Products are less stable because they have higher potential energy. And then we can also look at the difference between the potential energy of our reactants and products is our change in enthalpy. So in this case, did the enthalpy increase or decrease? Increase. And so is delta H positive or negative? Positive. This is the one I would draw on my notes. I'd label each axis, start out with the reactants. Activation energy and activated complex are things we'll talk about towards the end of the year, but it wouldn't hurt you to have them down. But the features you need to see here are how the reactants and products compare, what the axes are labeled, and how we can use this to find our change in enthalpy. So you guys go ahead and get down the information about exothermic reactions, and then we'll talk about them. Talk about exothermic reactions. So in exothermic reactions, as a reaction takes place, heat energy is what? Given off. So energy would be listed in the products because net, overall, energy is given off. What happens to the potential energy from reactants to products? It decreases. So who's more stable, the reactants or the products? Products. Products have lower potential energy, so they're more stable. So some examples of exothermic reactions. We've got combustion. Combustion gives off energy. Metabolism of glucose or oxidation of glucose, and also decomposition of hydrogen peroxide. This is a reaction I like to do because it's a simple reaction that you may have done in biology, and it's one where we can measure and actually look at the change in heat energy in a pretty safe way. So fingers crossed, we'll get to that this year. So how does this compare to the potential energy diagram for endothermic? Do we still start out with the reactants? Do we still end up with the products? Yes. But what's the difference? What happened to our potential energy from our reactants to products? It decreased. And then what happens to the enthalpy? Is it a positive or negative change? Negative. Now, one thing to note is activation energy is something we'll talk about way later, but there still is an impetus that's required for exothermic reactions to take place. So an input of some energy to get the reaction started. But what we're looking at is overall, throughout the reaction, the net change is a decrease in energy.